Hello, my name is Ruben Meyer. I'm presenting a joint work together with Hans-Arno Jacobsen called Hybrid Edge Partitioner, Partitioning Large Power Law Graphs Under Memory Constraints. Graph-structured data is everywhere around us, like social networks, web graphs, biological networks, and others. Here, graphs capture relationships between entities, like a friendship between users of a social network, or hyperlinks between websites, or links between brain cells. Graph processing systems analyze such large graphs and answer high-level questions like whom should I follow on the social network, or what web page is most relevant or important to my request, or how is the human brain connected and composed. So, in order to answer these high-level questions, we have to solve graph problems using graph algorithms. Now, real-world graphs can be quite huge. They can have millions or billions of vertices and edges. In order to scale graph computations, distributed graph processing systems like Spark GraphX or PowerGraph have emerged. They are able to spread the computation across many different compute nodes. In doing so, they impose an iterative compute model where a vertex state is updated based on the state of its neighbors in every iteration. To make such an iterative compute model work in a distributed fashion, the input graph is split into distinct parts that are loaded on the different machines. This procedure of splitting and distributing the graph is called graph partitioning. In our paper, we tackle a specific formulation of the graph partitioning problem called edge partitioning, where the edge set of the graph is divided into k equally sized chunks, or called partitions. In doing so, it can happen that a vertex is cut. That means incident edges of the vertex are spread across different partitions. Cutting through a vertex implies that that vertex is replicated on the different machines. Vertex replication induces synchronization overhead because the different states of the vertex have to be synchronized in the computation. The goal of edge partitioning now is to minimize the vertex replication factor, that is the average number of replicas per vertex. This way, the communication and synchronization overhead is reduced and the graph processing is becoming faster. Existing partitioners can be grouped into two categories. First, in-memory partitioners. In-memory partitioners load the entire graph into the system, into the memory, and can achieve very high partitioning quality because they exploit the view of the entire graph. The disadvantage of in-memory partitioning is the high memory overhead, which makes the graph partitioning step expensive. Contrary to that, there are the streaming partitioners, where the input graph is consumed as a stream of edges, and only one edge at a time is viewed at the streaming partitioner and assigned to a partition. This way, memory overhead is very low, because the graph is only accessed one edge at a time. However, the partitioning quality is lower because the partitioner only has a very limited view of the entire graph. In our work, we ask ourselves the following question. Can we get the best of both worlds, that is, low memory overhead, like in streaming partitioning, and good partitioning quality? Our contributions are as follows. We propose Hybrid Edge Partitioner, HEP, a hybrid system between in-memory and streaming partitioning, with a tunable trade-off between the memory overhead and the partitioning quality that is achieved. HEP is composed of two improved partitioning algorithms. First, NE++, a highly efficient algorithm for in-memory partitioning. Second, informed streaming, a streaming partition algorithm that exploits the partitioning state from the in-memory partitioning phase. Finally, we evaluate HEP on a large set of real-world graphs of up to 64 billion edges. Let me give a brief overview of how HEP works. HEP divides the input graph into two subgraphs A and B. Subgraph A is partitioned with an in-memory algorithm. Then subgraph B is partitioned with a streaming algorithm. This implies that only subgraph A needs to be loaded into memory. There are two challenges involved. First, how to divide the graph into A and B. Second, which partitioning algorithm to use for each subgraph. Answering the first challenge, we analyze the property of real-world graphs. These are also called power law graphs. The distribution of vertex degrees in a power law graph is highly skewed. There are many vertices that have a low degree, but only very few vertices that have a high degree. In other words, low-degree vertices constitute the majority of the graph. Now, existing partitioning algorithms like HDRF, a streaming algorithm, or NE, an in-memory algorithm, focus on reducing the replication factor of low-degree vertices. High-degree vertices are less important as they are only very few. We exploit that observation in HEP and divide the graph based on the vertex degrees. Edges incident to at least one low-degree vertex need high partitioning quality, so they are partitioned using in-memory methods. On the other hand side, edges incident to two high-degree vertices do not require such a good partitioning quality, so they are partitioned using streaming methods. High and low degree vertices are separated by a tunable parameter called tau. A vertex is considered high degree if its degree is larger than tau times the average degree of the graph. Else the vertex is considered to be low degree. In the given example graph, the average degree is 2. If we set tau equals 1, this means that all vertices with a degree larger than 2 are considered high-degree vertices. These are the red-shaded vertices in the example. Now the edges between the red-shaded vertices are part of subgraph B, whereas the rest of the edges are part of subgraph A. If we increase tau, we can see that the set of high-degree vertices becomes smaller, so does subgraph B, until all of the graph only belongs to subgraph A. Subgraph A now is partitioned using an in-memory algorithm called NE++. NE++ extends the neighborhood expansion NE algorithm with the following optimizations: graph pruning, lazy edge invalidation, efficient seed vertex search, adapted capacity bound, and skipping of the last partition. The latter two optimizations are not covered in the talk, but can be read up in the paper. Before we dive into the details of the optimizations, let me give a brief review of the NE algorithm. NE grows partitions subsequently by something called expansion. First, we start with a random seed vertex, V, and place it in a specific vertex set called core set C. The neighbors of the seed vertex are put into a secondary set S. All edges between vertices in C and S are assigned to the current partition. Now we perform an expansion step. An expansion step moves one of the vertices from S to C, and the external neighbors of that vertex are moved to S. We choose the vertex to be transferred from S to C as the vertex that has the lowest external degree. The external degree are the number of neighbors of the vertex that are not yet in C or in S. In the given example, the vertex number 7 is the one with the lowest external degree. It is moved to C, and its external neighbor is moved to S. This implies that there are new edges between vertices in C and S which have to be assigned to the partition. We would proceed with the next expansion step and so on until the partition has a sufficient number of edges. The first optimization of NE++ compared to NE is called graph pruning. NE loads the entire graph into memory. This can be achieved using the compressed sparse row data structure. This consists of two arrays, an index array and a column array. The column array contains the adjacency lists of all the vertices in the graph. The index array points to the adjacency list in the column array of the corresponding vertex. Now NE++ does not load the entire graph into memory. Instead, we exploit the division between high-degree vertices and low-degree vertices. So we skip the adjacency lists of high-degree vertices. We do not load them into the column array. Instead, we write out the edges between the high-degree vertices to an external file, which is later partitioned using a streaming method. This way, the column array can become much smaller. This saves memory. The second optimization of NE++ is called lazy edge invalidation. The NE algorithm keeps book about all assigned edges to avoid that an edge is assigned to multiple different partitions. This means that the edge is deleted or invalidated after it's assigned to the current partition. This is actually not necessary because vertices in C will not be visited in subsequent partitions. Therefore, edges between vertices in C are not critical. They can anyway not be assigned a second time, so there is no reason to invalidate these edges. Only vertices in S can be visited by another expansion of another partition, so the critical edges in terms of double assignments are only those incident to vertices in S. We exploit this property in NE++ by not removing edges between vertices in C. Instead, we introduce a cleanup phase after the expansion of a partition is finished and only clean up edges incident to vertices in S. The third optimization is efficient seed vertex search. In the NE algorithm, there's a random selection of the seed vertex. This can lead to problems if most of the vertices are already in the core set C. In that case, it's hard to find a suitable seed vertex, and there are many random jumps until a free vertex is found. In NE++, we perform sequential scanning of the vertices by their ID to find a free vertex. This way, every vertex is visited at most once in the overall seed vertex search. After subgraph A has been partitioned using NE++, subgraph B is partitioned using streaming partitioning. HEP here uses the HDRF scoring function. This works as follows. For each edge, the partitioner computes a scoring function for each partition. The score mostly depends on the replication of the vertices in the edge. A partition gets a higher score for an edge if there are vertices of that edge already replicated on that partition. In the given example, the yellow-colored vertex of the edge is already replicated on partition P2, so partition P2 gets a high score. Finally, the edge is assigned to the highest scored partition, and the vertex replication state is updated. The optimization in HEP is that we initialize the partitioning state from the in-memory partitioning NE++. This way, we avoid the cold start or uninformed assignment problem of streaming partitioning, where in the beginning of partitioning, the vertex replication of all of the partitions is empty. We evaluate HEP with regard to different partitioning metrics. First, the replication factor. Second, the partitioning runtime. Third, the memory overhead of partitioning. Further, we perform experiments on distributed graph processing runtime on a 32-node Spark GraphX cluster using three popular workloads: PageRank, breadth-first search, and connected components. As baseline partitioners, we choose competitive in-memory and streaming partitioners from the literature. Finally, we have a large set of real-world graphs we perform our evaluations on. First, let us analyze the replication factor. We evaluate HEP for different settings of tau and compare it to the streaming partitioners in the blue color as well as the in-memory partitioners in green color. We perform experiments with different numbers of partitions. We observe that HEP yields a better replication factor than streaming partitioners and a competitive replication factor to in-memory partitioners. Further, if we decrease tau, the replication factor of HEP increases as the portion of the graph that is partitioned with streaming partitioning increases. In terms of the runtime, we observe that HEP has a competitive runtime to the streaming partitioners as well as the in-memory partitioners. The only exception is hash-based partitioning, which is the fastest. The runtime of HEP increases with a decreasing value of tau as the portion of the graph that is partitioned by streaming partitioning increases. Streaming partitioning is more expensive here as it involves computing a scoring function on every edge for every partition. In terms of the memory overhead, HEP has a lower memory overhead than any of the in-memory partitioners. Further, by decreasing tau, we can decrease the memory overhead of the partitioner. So the memory overhead of HEP is tunable by setting tau. This is novel. No other partitioning algorithm can achieve a tunable memory overhead. In terms of the graph processing runtime, we observe that a graph partitioned with HEP shows a low runtime in terms of page rank, BFS, and connected components calculations. Often HEP achieves the lowest end-to-end runtime composed of partitioning time plus processing time. There is only one exception, which is the connected components algorithm, which is a fast-running algorithm. If the processing algorithm is very short-running, it is better to perform quick partitioning using hashing, because end-to-end it does not pay off to invest more time into partitioning. Let me conclude the talk. In this talk, I've shown that graph partitioning is an important but a memory-intensive problem. HEP achieves both low memory overhead and high partitioning quality. It is a hybrid between in-memory and streaming partitioning. HEP has a tunable trade-off between memory overhead and replication factor by setting tau. HEP includes NE++, a faster and memory-efficient extension of the NE algorithm. In future work, we consider generalizing the hybrid partitioning approach to hypergraphs. This concludes my talk. Thank you very much for your attention, and please consider the link to the GitHub repository where you can find the source code.